Today we're going to look at categories of orderings. This might be interesting from at least two point of views. Point of view number one is I know a little bit about category theory and I'm interested in some examples. I want to see what's happening. Or maybe I'm a bit bored of category theory just being introduced in general and I want to see how it arises in some area of mathematics. Second point of view would be, well, I'm interested in orderings. I'm working with order relations and constructions around them, and category theory is a way to help me keep things organized and neat in my head when talking about orderings, and help me use language from other areas of mathematics, use skills from other areas of mathematics, and apply them to this new area of order theory. Regardless, let's talk about both what categories we're looking at and what orders we're looking at, and of course they're going to correspond to one another. So there's a lot of different types of orderings. This is not going to be a good introduction into that. I'm just going to list possible properties that we would want. So an ordering, is an order relation on a set. So this is a set of things that we want to order. I might have X and Y in here, and I want to think about what it means when X is smaller than Y, and in total, how this relation, what rules this relation should follow. Here are some rules. Because I'm looking at this, I'm using this symbol on purpose and not this symbol, even though this is almost more natural or more common in many areas of math. This is called a non-strict order relation, which basically means we don't have that X is smaller than X. So this is called anti-reflexivity. What else would we want? Well, for it to honestly even be allowed to be called an order, I feel like it should be transitive, which means this. I'm often going to be drawing orderings as, little dots and arrows between dots. And what I mean is that the object pointing to another object is smaller than that object. And transitivity basically means that, if I draw something like that, it's obvious that this arrow also exists. What's another rule? Another rule you might know is asymmetry. We don't need asymmetry here. It's a consequence of anti-reflexivity and transitivity. What we might want is connectedness. So this is pretty straightforward. This means that any dots that I draw must be connected with each other by some form of arrow. It doesn't matter in which direction. But we can't not have arrows between dots. So one way to write that down would be X is equal to Y, or X is smaller than Y, or Y is smaller than X. Depending on what meta theory we're using, it might be nice to write this in a slightly different, logically equivalent way. And finally, we might ask well-foundedness of our order, which means two equivalent things. One is the following: every subset of X has a minimal element. Equivalently, we could also say, depending on the meta theory, we could also say that X has no infinite descending sequences. Infinite. All right, you can take a moment and think about why that's the same thing. these two properties, an order that satisfies these two properties is called a partial order, a strict partial order. If it is also connected, it is called, I guess, a linear order or a total order, or I don't know, I'm probably going to say strict. It is possible to look at strict partial orders that are well-founded but not connected. We're just not going to do that right now. We're going to look at those that are all four of these things. And these are known as well orders. So if you're familiar with the ordinals from set theory, those are well orders. All right, so we have these three theories of orders, and now we're going to look at categories that correspond to these orders. So we're going to look at the following three categories: PO, LO, and WO. So partial orders, linear orders, well orders. The objects will be all possible sets equipped with all possible orders such that these two rules are satisfied. Same with the linear orders and the well orders. So now we have the objects. Of course, we need the maps. Every category has objects and maps between them, or morphisms between them, or arrows between them, whatever you want to call them. And in this case, it's going to be the same maps in every case, or at least the same definition for maps in every case. So the maps are functions that go from one order to the next order, such that if I have x smaller than x prime, then f of x is, well, should have just started a new page, then f of x is smaller than f of x prime. Of course, I should have been a bit more neat and differentiated between these orders. So these are, because they are different sets, they have to be different orders. Doesn't make any sense otherwise. But I won't always differentiate. It's often just clear from context what order I mean. Today, we're going to focus on looking at monics and subobjects. So, super short recap. A monic in a category is a map F such that precomposed with any two maps from the same object, if these two compositions are equal, then so were these two maps. Then these maps were the same map, or not. So in the category of sets, which I'm going to denote like this, a map is monic if and only if it's injective. This is sort of where the idea comes from, maybe. Of course, it doesn't make sense to say this in general, because injectivity might just not be a thing you can talk about depending on the category. In our category, in our three categories, injectivity is something that we can talk about, because we're looking at something that, if I remember correctly, is called a concrete category, which essentially means that it's built upon set. We took sets, we equipped them with an ordering, and then we made these sets and functions between them. We took real functions, we didn't take some other weird thing as our morphisms. And so it is worth thinking about what the connection between injectivity and being a monic is, especially because just looking at this definition of order preserving, we might perhaps suspect that order preserving maps may already be injective. because, you know, it looks a lot like the definition of an injectivity, or at least one possible definition, the one that I like the least, where if we replaced the small events with unequals, then that would be the contrapositive to injectivity. So, question number 1. Are order-preserving maps already injective? You know, not monic yet. Let's look at injective first, and then we'll think about monic. So, let's look at the argument that we were thinking of when we wondered whether this might be true. So the argument would be, well, suppose that f of x is equal to f of y. Then, if the order is connected, we can say that either x is greater than y, or y is greater than x, or x is equal to y. One of these three things must happen. If this happens, we are already done. That's injectivity. So all that is left is to show that these other two cases can't happen. Well, if we had this, then the consequence would be this. Sorry, other direction. Which, you know, would contradict our assumption. So this is not the case. And the same goes for this one. So yeah, it works out, assuming connectivity. So the answer is in LO and WO, all morphisms are injective. We're not done. In partial orders, what if they're also injective, but we just didn't manage to get a proof? Actually, there is a counterexample. Check out this map. We have this order, and we're going to map it to this order. This is, you know, of course we have to do it right, so these pink elements go to the pink element, this orange element goes to the orange element, and both of these maps, of course, are matched to the only available map. This is order preserving, this is not an injection. So this isn't the case. All right, now we've been talking about injections, but actually what might have been more interesting is to talk about monics. So in set, we have that monics are the same as injections. Is this the case in our categories? So in O, L, O, O, R, monics equals injections. Well, in LO and WO, this would correspond to asking whether all maps that we have are monics. I'm going to keep the answer short. Yes. Of course, here I mean injections that are order preserving, not any old injection. An injection is not necessarily order preserving. So, because these three categories are built upon set, as I said before, an injective map is also a monic. This is the case because of how we built the category, because it's a concrete category and we took functions as our morphisms. The other direction is not always the case, even when we have these concrete categories, but in this case it works out because we have something called that I'm going to call the free object on the singleton. So basically we have the singleton set, which has one element, and we can equip this with an ordering, namely, there's just no order. And using this object, we can translate the definition of monic into an injection. So I'll leave that to you. It's not very hard though. It's the same idea of how you show this in this equality in set. That's exactly how you show it for our categories using this singleton. If this singleton didn't exist, it might be trickier. Or in categories where you can't make such a freed object, it might not be true. But in this category, it is true. All right, so we've kind of figured out the monics. Yeah, the monics are injections. There's nothing new. And in the case of LO and WO, we can not even wonder if something is a monic. We just automatically know all the morphisms are monics. What about subobjects? Subobjects are isomorphism classes of monics. So if I have two monics of the same object, then actually let's give them names, S1 and S2. S1 and S2 are monics, have monics into the object X, and if there is an isomorphism between them such that this diagram commutes, then they correspond to the same subobject. So it's sort of subobject is a class of monics into X. What I'm interested in is the subobject relation. So basically, given an order X and an order Y, I'm going to define a new ordering, which might be a bit confusing. I'm going to write it like this. This inequality is not at all related to these two. It's completely different things. Well, they're going to connect in some way. But I'm not trying, I could have denoted it in some other way. So, this stands for there is a monic between X and Y in our category. So now the final question I want to ask for today is, what properties does this order have? It's a very natural order to look at. It's the order of subobjects. We could look at a single object in our category and think about the set or the thing of subobjects. I was about to say lattice, but it's probably not a lattice. And look at what properties this set has, or we could just sort of be okay with looking at orderings on things that are not sets and just say, well, if I just look at the entire category, this relation is defined on the entire category. What properties does it have? So that is the last question that we're going to work on today. So the answer is probably going to be, it depends on which category for PO, LO, WO. Let's list the properties that we might have. Now we have a non-strict order relation. So the fact that I'm denoting it like this is because, if I have the same order, then the identity map is order preserving and is also a monic, regardless of which of the three categories. So we have reflexivity. Actually, let me use uppercase letters so that we don't get confused. What else do we have? Well, if I compose two monics, I get a monic. So I have transitivity. Again, regardless of which category. That's pretty good. That's already sort of, I'm okay with calling something a pre-order if it satisfies these two things. What about symmetry? So I'm going to add a question mark there. Here we already know this is true. Here we're not sure yet. So is it true that if x is smaller or equal to y and y is smaller or equal to x, that then the two are the same? If this were the case, we would be allowed to say that this is a poset, a partial order. Well, no, let's not say poset since it's not necessarily a set. Let's say a partial order. So honestly, just for neatness reasons, it would be kind of nice if this relation for PO satisfied that it was a partial order. That would be kind of neat, right? However, there's a counterexample. It might be fun to pause the video and try for yourself. This poset, which you could also think of as the poset of natural numbers. And then we have a poset that looks the same, but it also has another element. So these are two different posets. So obviously this embeds into here. I can just take this whole chain and map it to this chain right here. What about in the other direction? Well, actually, I can take this object, this element right here, and map it here to the first element of the other partial order, and then take the chain and map it to the rest of the chain, sort of removing the first element. So this works out. So for PO is not symmetric, which is not, just so you know, it's not the same as asymmetric. Okay, what about for LO and WO? For LO, this is also not the case. And there's a fun counterexample there as well. And we could have started with that one, but I find it a little bit, I find the PO one a little bit simpler and more pleasing. For WO, it's true. Just going to tell you that for now. We're going to get back to it. For LO, you can pause again and think about the counterexample. So the counterexample I have is, well, in Q, I'm not going to draw stuff anymore because I want things to be very dense, and that makes it hard to draw. In Q, I'm going to look at the interval 0, 1 and the interval 0, 1 without the edges. So obviously I can embed this like this. So Q with the usual ordering. This is going to be order preserving. What about the other direction? That seems like the strange one. So obviously I can't map 0 to 0 and I can't map 1 to 1. But what I can do is, here I have 0 and then 1. What I can do is I can map 0 to 1/2 and 1 to, I don't know, 0.8. Doesn't really matter. and scale the rest of the interval between them. So this was not very formal. Feel free to think about it and figure out why it actually works. But this is an injective order preserving map, so it's a monic. So we have these two directions, but we don't have a bijection between these two things. But no bijection. So okay, I'm saying it by the by. Also, I should not write bijection. But no iso. So not symmetric. Which is, you know, quite a crazy order to have, to be honest. If you have cycles like this, that's not something you see a lot in order theory. That's why we call it a pre-order. The partial order is sort of what I'm used to seeing as the sort of lowest level sensible order. So it's not a very sensible order. I just realized I forgot to say that here I mean isomorphic, of course, not equal. All right. Two more properties are possible. It could be connected, and it could be well-founded. Again, there are counterexamples for connected, and there are counterexamples for well-founded. No for PO and LO, which could be fun to find. If you want to be quick, you can just find a counterexample for LO in both cases. Connected means, again, that either given two orders, either x is smaller or equal to y or y is smaller or equal to x. Well, let's see. The smallest counterexample I can think of is that if we have an infinitely descending chain and we have an infinitely ascending chain, then we're not going to be able to embed in either direction. It's just not going to work. What about well-foundedness? Well, well-foundedness, I think we can steal a counterexample by using this example with the 0-1 interval. It's honestly quite funny to think about well-foundedness when something is not symmetric. It's kind of a weird thing. Maybe you could even just take this whole cycle if you really, if you did the chain properly. That's kind of funny. I think if we could take that example, we could start with the interval 0-1. And then we could notice that this is, we can embed 0-1 into that. We already saw that before. And actually, let me write that in another way. 0 and add a 1 to it. Actually, we can also add 2 to it, because all we have to do is, in this fraction of 0-1, if we add a 2, then, let's just map the 2 to 0.8, and we're going to map the 1 to 0.7, and the 0-1 to, 0 to 0.6, if that makes sense. Like, we can arbitrarily scale the interval 0-1 as much as we need. And so on. So there is an infinite descending chain, both in PO and LO. All right. Yes, for WO. So it's quite fun to prove this. So what we can conclude is that for WO, this forms a well order, a non-strict. Which is, it's a bit sad that it doesn't work out for all the others, for PO and LO, and it kind of, makes you think, well, maybe this wasn't the right map to look at. Maybe I should have looked at maps that are not only order preserving, but also look at initial segments. And then this would work out. But I don't know, these were the categories that I'm interested in right now. And it didn't work out for PO and LO. But it's quite funny that as soon as you add well-foundedness, the well-foundedness not only preserves the well-foundedness, but it also fixes everything below. And I'm not going to go through that proof, even though I strongly encourage trying that, but sort of give the core idea, which is something that I would call an attempted embedding. Between well orders. So given two well orders x and y, or two orders x and y in general, how would I attempt to create a monic between them? Well, honestly, the whole reason these properties didn't work before intuitively is kind of like, well, I don't have anything to grasp. Like even if, for instance, with the symmetry, even if x is smaller or equal to y and y is smaller or equal to x, if I want to construct an isomorphism between them, I need to build this isomorphism somehow. There's nothing that I can really grasp. But if I have a well order, then I do have something that I can grasp. And I can do it as follows. I could start with m1, or let's call it m0, as the minimal element of x, which exists because it's a well order. And I'm going to say, well, I'm going to map the minimal element of x to the minimal element of y. Let's call it y0. Okay, next, I'm sort of going to define this by well-founded recursion. So now I'm going to look at x without mo. This is also going to have a minimal element. Let's call it m1. And then I'm going to say, well, map this to the smallest element in y without y0. Let's call it y1. And so on. I just continue like this. So the reason I call this an attempted embedding is that this is only going to work if we run out of elements. If we run out of elements in x, if, you know, x without, now here we have mo, m1, and so on. If we finish the elements in x, then we're done constructing the function. But if we're not done with the elements in x, but we finish the elements in y, then we failed making a function because we suddenly have an element in x that cannot be mapped anywhere. So that's why it's an attempted embedding. So let's call it E is a partial function from x to y, which means that sometimes it might be undefined. And it's going to be defined as the minimum. So I'm just writing down formally what I already explained. The minimum of all y's. And now I'm deleting the things that we've already done recursively. So such that everything that we previously looked at is smaller than y. So, when would it be undefined if this is the empty set? Then if this is the empty set, then it ends up being undefined. Let me scroll so that you can see it. There you go. This is what you can use to prove all those facts about well-founded orders that I mentioned before. You know, for instance, if I had this again, and I wanted to show an isomorphism, I'd be like, okay, let's just take E as this isomorphism. Let's not even use F and G. Let's just look at E and the other, you know, E prime, E in this direction, and E prime in this direction. And this is going to be the isomorphism. Why do we need F and G? Well, F and G are always going to be witnesses that this set is not empty. So the fact that f and g exist are gonna make sure that E and E prime are well defined. Yeah, so that's how it works out. To summarize, I think the most fun fact is this. And we've also found out what monics look like in our categories. Yeah. Using the answers to these two questions. All right. Cheers.